Okay, this is for the complexation experiment. So pseudoephedrine with beta-cyclodextrin. So we're doing an isothermal titration calorimetry measurement of that complexation for both SS and RR pseudoephedrine. So it's different method, same information. We're actually using the single method. Different groups are going to do SS and RR. So each group is going to do one of those so that we can compare. We want to get thermodynamic information out of this complexation. So we want to get the equilibrium constant for the complexations, the delta H's, the delta G's, the delta S's. We would like to know what is the driver of the complexation. Is it entropic? Is it enthalpic? Is it something like hydrogen bonding? This one is a little bit different in that we're not doing a formal lab report for this. We're doing a group PowerPoint with voiceover. So that should cover some of the theory behind isothermal titration, how you set up the experiment, and then results and discussion. What did you find in terms of the thermodynamic quantities, and then what does it mean for the complexation? What's the driver of the complexation? Are there differences between the SS and RR? So you will have to share results a little bit, but we have one ITC, so that shouldn't be too difficult. So beta-cyclodextrin is this molecule. It has a handful of, actually this is alpha-cyclodextrin because that's what I can find a picture of. It has a number of sugar molecules in a ring that gives you this nice sort of open-ended cone into which you can stick hydrophobic things generally. And you have a lot of these CH2OH groups and OH groups that stick up on the tops and bottom of beta-cyclodextrin. It can be used, or it's considered as a possibility for delivering drugs because, like I said, you could put things in that pore in the middle to transport them if you like. Beta-cyclodextrin has a large enough cavity that both of the pseudoephedrines will stick in there nicely, so we're going to measure that. We're doing ITC. So ITC stands for isothermal. Isothermal means constant temperature. Titration, so we're going to be adding things in specific amounts over the course of the reaction. And calorimetry, so we're measuring heat flow. In particular, ITC works by measuring the current required to keep the temperature constant as a function of time. So we're measuring the change in current, D capital I, dt, current versus time. The heat is proportional to the current, and we're operating under constant pressure conditions. So Q and H are the same thing, dQ and dH are the same thing. So if we can integrate Q, we will get delta H, right? Change in Q, we get Q. Then from change in H, we'll get delta H, the state function portion. There are some issues. This is extensive, so it's not intensive. So the more things you put in there, the more heat you get. So we need to know heat flow going on for everything, or we need to at least be aware about it. Do we have dilutions? Do we have other equilibria going on? It's a titration, so we're assuming A plus B in equilibrium with C. And the Q we're after is NC delta H, so the moles of C, the complex. The moles of the complex depend on the equilibrium constant. How much of A and B react to form C, how much stay unreacted. So we can find K by doing concentration of C over concentration of A and B. So concentration of the complex over concentration of beta-cyclodextrin and pseudophed. We want both delta H and K, which means we need moles of everything, essentially. It's a titration. So we're adding aliquots of A to B or vice versa. It's an automated titration in the ITC, so we're going to fill up a syringe and it will automatically add those volumes of the syringe into the reaction vessel. So we know those volumes very well. If we know the volumes, if we know concentrations, then we can find moles easily. And most of this math is done in the software for the ITC. However, the accuracy of your results are going to depend upon how well you know your concentrations. So making your solutions is going to be important. You want to pay attention to that. And you want to make sure that you put the actual concentrations into the software before you do the fitting. So we'll run a series of injections. The computer will guide you through fitting the results of that to get the best values for K and delta H. From K, we can get delta G using a hopefully very familiar equation. We have delta G and delta H, we can get delta S. Also from a very obvious, familiar, friendly equation. And that will give us information about the complexation for those. Once we have those thermodynamic quantities, we can compare SS to RR, and that should be fairly straightforward to analyze. Manuals for the ITC and the software are on Canvas. There's also hard copies down in the lab for those. ITC does take a little bit of practice, and it can be slow. On the bright side, once you set it up, it will run on its own and stop on its own. So it is possible to set up a run at the end of lab and let it go overnight, and then come in and clean the ITC the next morning and look at results. So it can run on its own. Good luck.